morning. Welcome to the last day of conf. We'll be talking about the amazing Turing machine. It's a pure Splunk implementation of a Turing machine running the popular Splunk language. And it's not using any custom commands, it's just pure Splunk. And to give you a quick demo of what I'm actually on about, I've built a status dashboard for the machine itself. I've preloaded a bit of code, and I will now start the actual clock so the machine can get going. It will now run one iteration every second, and to get finished in time, I will just tell it to run 50 steps per clock beat. And what's happening now is the dashboard will incrementally tell you the current state of the machine. It's not finished yet. It doesn't care about its input. It hasn't produced any output yet. That's like the high-level view into the state. And down here we've got the actual code that it's running. We can see where in the code it's actually working. That instruction pointer will bounce around because these square brackets are loops. We've got the infinitely long data tape. And if you're familiar with Turing machines, if something is infinitely long, it always feels good. So this will grow until my laptop runs out of physical memory. And at some point, that finished indicator will move to 1. And we'll see some lovely output. And I hope I've almost talked long enough so we can start seeing some output. Awesome. So as you can see, the machine has produced our highly valuable output, and it has stopped itself, and it's happy. So after the initial demo, what have I actually built? What I've built is a programmable machine. So there's an interface to change what the machine is doing. For example, we can do an infinite loop. And again, anytime something runs infinitely often, it always feels very Turing-y. What that code actually does is increment a data point and loop while that data point is not 0, which will run infinitely. But to do a more useful example, let's add 2 numbers. And I would like to get 2 one-digit numbers from my audience. 2 and 5, okay. I will do 5 and 2, okay? That way it will run faster. But 2 and 5 will work all right. So what this programming interface does is reset the state of the machine to an empty data tape, make the machine start at the beginning, give it some input, reset the output. And when we return to our actual machine, and I will make that run once a second, but go one step at a time so we can see what's actually happening. So you should pay attention to the data tape down here. It is reading its input, so 5 and 2 have been consumed. They're now living on the data tape. And the loop up here is now starting. It will basically decrement this by 1, move to the left, increment it, return to the right. Repeat while that is not 0. It is now 0, we're missing 1 increment. There we go. Now it will return, see, oh, it's 0, and then do the final output at the end, the dot character. So at some point we should see an output happen up here, hopefully a 7. Awesome. And now the machine should realize it is finished. Ignore that. It has realized it's finished, and it has stopped itself. So it doesn't keep running without anything useful to do.
Yeah, that's awesome.
Thank you. So that's lovely, but how does it actually work? Tiny disclaimer, I've cheated a little because it only really works by using either the dashboard refresh to get a new step or by using the scheduler. What I've built is an implementation of 1 step and a lookup file to store the state. And that 1 step is broken into several micro steps. If you're familiar with CPU design, that's basically how you'd build a CPU. You get one huge step that runs every clock, and for each sub-part of that, you would separate out the different concerns. So I will load the state, I will understand the state, I will take care of the new instruction pointer, I will take care of the new data pointer, if the instruction changes the instruction or data pointer, depending on what instruction currently is running. I will possibly write new stuff to the data tape. I will possibly read or write stuff to my input or output, and I will write back the state into the lookup file. What's missing here, I've left out the final output lookup, so we can iterate on the same state without actually writing it back. What this does is the opposite of parsing. Basically, that's a parse, that's a format. And let's look at some of these instructions individually. So when we've got our state, it's basically the line we've seen in the machine itself. And I will just quickly reset it because that's the finished state. Let's do add two numbers. Let's do 2 and 2. Reset our machine. There we go. So when we read the state, it will be the initial machine state. Awesome. So when we just parse out the different parts of that state, what's happening is I'm parsing out the different steps of code. So later I will then use the instruction pointer to pick out the correct instruction. And I've parsed out the input into a multi-value field as well, so I can access that like an array-ish. And since you're all highly interested in SPL, it's just one big eval doing formatting. So for example, it will split the data by a carriage return. So this code formatting is actually semantically necessary, because when you write out an MV field to a lookup, it will be separated by carriage returns. And then I'm doing lots and lots of just, for example, find the correct code at my instruction pointer, or split up the code in that list. Just prepare my input state to be usable. So let's see, our first command is a comma, and the parsing has told us the step we have to do right now is a comma. Comma is read input. So when we set the instruction pointer, we'd expect it to be just an increment. Take the next command. So the instruction pointer should go up by 1 if I add that additional microstep. And it does. There's lots more stuff happening because adding the instruction pointer is actually the hardest part of the machine. Because if you've got simple commands like the input or output, you just need to increment. But if you have those two square brackets, they're loops. So you have to figure out jump to where and do you jump or not. And that's the most interesting part of the code. So ignore the 2 lines up here. We already know these. That's the parsing. Anything, let me scroll to the right place. Anything from this MV expand is our set the instruction pointer code. And as you can see, there's lots and lots of stuff happening. To sum up in natural language, what I'm doing is I am numbering my instructions in both directions. So then I can use the opening and closing square parentheses to link them up in pairs. Because if there's a closing parenthesis, I have to know which opening one is the corresponding one within that pair. There could be pairs within it. It could be contained in bigger pairs, so I have to link up the correct ones. And that's some fiddly number pushing, basically. I'm not going to go through every single command in here. Feel free to download that app. It is available on Splunk Base. Just the general idea is to run through with stream stats, give us a count, and then basically count up or down when I see opening or closing parentheses, so I know at which level down that tree I am currently. And if I sum up those plus or minus ones, I just get the depth. And I have to do that in both directions. Keep some markers so I know where I actually am. Basically reverse, do the counting again, reverse it so I'm at the correct point. And this lovely little where will then go in and select the correct future code point if I'm doing one of those looping commands. So if I'm in a closing parenthesis and I'm at the right point, or I'm at an opening one, or I'm at the different marker. So this is the reverse marker for closing. This is the forward marker for opening. Or if I'm not doing one of these commands, so or the true one down here, that XOR is actually the way Splunk expands macros. So that actually just says not this part. It's just being expanded in a fairly ugly way. And since I have filtered down to the correct command, I can just pick the top one. And the top one will then tell me whether I have to increment my instruction pointer. If I'm at an opening parenthesis and my current data is not 0, then I have to proceed into the loop. Basically, in programming terms, I only have while current data point is not 0. And if it's not 0, I will jump into that while, so I will increment my pointer by 1. If it's not greater than 0, then I will jump to the count I have produced up there, which will tell me what the first command after the corresponding closing bracket will be. So I've basically kept the pairs in every single line, and by selecting the correct line, I know I have the correct pair. If I make closing parentheses, it's the reverse. If my data is 0, I will just advance past the closing parentheses, and if it's not 0, I will jump back. And for the closing row, the count will tell me where to go back. For the opening row, the count will tell me where to jump into. And in any other case, I will just increment it by 1. I will quickly move through the rest, just so you've seen it all. This is the end of the instruction pointer code. The data pointer code is really simple. There are 2 commands to move it forward or backward, +1 or -1, or do nothing. Setting the actual data is just a tiny bit complicated because the Splunk language is supposed to work on unsigned bytes. So I just have to implement the rollover. If I do 255 + 1, I get 0. That's basically anything that's in there. Setting my data tape depends on whether I'm doing input or additions or whatever. That's just basic evals, nothing too complicated. These are the input-output steps. If I'm doing an input command, read something from the input tape. If I'm doing an output command, write something out. And this down here is the final write stuff out. So it selects the correct set of fields in preparation to write that out to tape, or rather to lookup, because we don't need all those temporary fields. And to wrap up, that machine is available on Splunk Base since a couple of days ago. 34 people have already downloaded it, so feel free to use it. It can run literally anything if you have the time. Awesome, so thank you for listening, thank you for tuning in, and we'll see you next year.